bell ringer question. Question number 1. If you're riding on a bus and you throw a ball straight up from your point of view, what does the path look like? Cody, what did you say?
I said, my point of view, you throw the ball up in the air, and the ball will go behind you. That's all I said.
Go in the air and the ball would go behind me. So you're saying that if I'm riding on the bus, I throw it up and the ball does that?
Yes.
Okay.
You made it.
Did I just make it in your bag? Yeah. That's awesome. All right. So, I made it in your bag. Yeah, total coincidence. All right. So, okay. He says that. How many agree with him? How many agree? He said that the ball would do what you just saw. I throw it up, the ball will go behind me.
I didn't necessarily mean you just throw it.
Well, I know, but I throw it up and the ball goes backwards. That's what he says. You agree?
Well, no.
All right.
It would appear to be that way.
It should be that way.
Anybody else have a different view?
No one's agreed on that.
It's going to go straight up and straight down? That's what Christian says. Who agrees with Christian? Okay. Well, let's see. If I am on the bus and I'm moving this direction, okay, and I just throw the ball straight up, then from my point of view, the ball is going straight up and down. Okay? If I'm just throwing it straight up, from my point of view, it's just going straight up and down. It's no different than if I'm standing here like this throwing the ball up and down. From your point of view, however, what's the ball doing?
Going forward.
That's question 2. From your point of view, it's going like this, right? Which means, did this ball do anything different whether I'm throwing it like this and walking or whether I'm throwing it... Now, did the ball do anything different whether I'm looking at it or whether you're looking at it?
No.
Did it?
Yeah.
Does it do anything different depending on who's looking at it? No. So, what's different? It's not the ball, it's the point of view. That's what we're going to talk about today, is reference frames and point of reference and how we describe motion based off of these frames of reference. Okay? We're going to do that through a little activity. So I'm going to explain to you the directions for what you're going to do, and then we're going to do it real quick. Okay? Go ahead and cut it. We're going to be talking today about relative motion. Relative motion is one of the basic, most important principles for our study of mechanics and physics. Because if you do not understand relative motion, then the rest of what we do is going to be kind of complicated. All right? Oftentimes. Now, a lot of times people hear relativity and they start freaking out thinking, I have to learn about that. It's so hard. I mean, Einstein was the super genius guy, and he figured it out, but I'm not that smart. Okay, that's not what we're doing. We're not talking about Einstein's relativity, but we are talking about one of the basic principles that Einstein based his theory of relativity on, and that is that motion is relative to the observer. Okay, we have to talk about motion in terms of the observer. Where is the motion being defined? A couple of weeks ago when we defined motion, first off, we defined motion as a change in position with respect to time. Okay? That's how we defined motion. Change in position. How do I know my position changed? How do you define your position? If motion is a change in position, how do we define position? Yeah? Well, that's saying, left is not right, so right must not be left. Okay? No?
Direction?
It's not really a change. How do you know your position? Where are you right now?
Here.
You're in a chair. You're on your desk. So you are defining your position based off of an object. Where are you? On a chair. All right? Or at a desk. Or in a classroom. Position is defined based off of a location relative to something else. Make sense? Okay? So this ball it has a position, right? It's above the ground. So, or it's below the ceiling. Or it's to the left of the wall. Or that wall. To the right of that wall. So its position depends on what we are measuring it against. That thing we measure it against is what we call the reference point. And in order to define motion, we have to have a point of reference. Or a frame of reference. And everything that we do in physics depends on what that point of reference is. We have to define what our point of reference is. For example, are you moving right now? Are you? Well, when I say you, I mean like your whole center of mass body. Are you moving right now?
Yes.
The correct answer to that question is relative to what? Because if I say, are you moving relative to the earth? The answer is no. Because relative to the surface of the earth, your position is not changing. Because you're sitting in your chair is sitting on the floor is attached to the building is permanently attached to the earth. So relative to the surface of the earth, you are not moving. Relative to the sun, you're moving hundreds of thousands of miles an hour. Because we're sitting on the surface of that earth, spinning in a circle on that earth, and that earth is spinning around the sun at hundreds of thousands of miles per hour. So, depending on what our reference point is, it completely changes how we describe our motion. If we're talking about the surface of the earth as our point of reference, we're not moving. We're talking about the sun as our point of reference. We're all moving very, very fast. Does that make sense? Now, the reference point is something we have to define in all situations, and there's one very important thing you need to know about the reference point. Because of what the reference point is, the reference point cannot move. Your point of reference, by definition, cannot move in any given situation. And you're like, well, how is that possible? Well, think about it. If I define my position by where I am with respect to a reference point, okay, let's just say that this baseball is the reference point. Then my position is based off of how far I am from the baseball, right? How far is the baseball from the baseball? 0. All right? How far is the baseball from the baseball?
0.
Still 0. How far is the baseball from the baseball? So if all positions everywhere are measured based off of where they are with respect to this baseball, does the baseball's position ever change? No. All positions are measured off the position of the baseball. Therefore, the baseball is 0. Always. Okay? Our reference point is always 0. Make sense? So the reference point cannot move. So, and here's the thing about the reference point. It's absolutely, completely arbitrary. You can choose whatever you want to be the reference point, as long as you hold it constant throughout the entire situation. As long as you maintain the same reference point through the entire situation, anything you want can be your reference point. So, if this baseball is the reference point, I can move the world with a flick of the wrist. You ready? Just did it. Yeah, want to do it again? Boom. Because what did we say about the reference point? Reference point,
It's always zero.
it's always zero, so it cannot move, right? So the reference point can't move, the rest of the universe just moved. You go home and tell your parents, hey, I learned how to move the world with a flick of the wrist in physics today. You know, and they'll look at you like you're crazy and, probably have me fired or something. I don't know. But that's the reference point. Now, in order to talk about relative motion successfully, you have to have what we call a frame of reference. Every situation needs to have a frame of reference, or a reference frame. So sometimes I'll say frame of reference, sometimes I'll say reference frame. Those are the same thing. It's just a matter of semantics as to which way I say it. But a frame of reference will always have two things. Okay, every frame of reference that we ever do will always have two things. It will have a defined point of reference, or a defined origin, 0 point, a defined reference point, and it will have a coordinate direction. So reference frames will always have a defined reference point and a coordinate direction. All reference frames will have those two items. So, we've already talked about the reference point and our point of reference and how to get that. So now let's talk about what do I mean by coordinate direction. So remember last week we were talking about motion and direction being positive or negative, right? So positive or negative. So a coordinate direction defines what the positive direction is. Okay? So if I'm talking in a normal place, I have to, or a situation, I have to say, well, this is what I'm referenced to, and this direction is positive. Okay? So that we can define whether or not I have positive velocity or negative velocity, or positive acceleration or negative acceleration. I have to know what the positive or the negative direction is. Okay? Now, you're probably sitting here thinking, well, if it's arbitrary and we can change for every situation, then we're going to have to define a frame of reference on every single problem. How many of you are thinking that? You are now because I said it though, right? Yeah. You're like, oh my gosh, we're going to have to find a frame. Situation, we have to define a reference frame on every situation, technically. But to make life easier, we in the world of physics have come up with what we call our conventional reference frame. And so what that means is, unless I tell you otherwise, this is the reference frame. Okay? So every situation we talk about is going to use the conventional reference frame unless I tell you, in this situation, my reference frame is different. Okay? So here's what the conventional reference frame is. Since all reference frames have to have a point of reference, on the conventional reference frame, our point of reference is the surface of the Earth. So, unless I say with respect to something else, or the reference point in this situation is blah, unless I tell you that in a problem or in a situation, you will always assume that the ground is your reference frame. Okay? Now we have to define our coordinate direction. Well, there are three coordinates. You have x, y, and z. Okay? The horizontal plane is the xy plane. The vertical is the z. Okay? Now, so we have to define what is the positive x, what is the positive y, what is the positive z. Okay? In the standard conventional sense, unless I say otherwise, moving to the right is positive. Moving forward is positive. Moving up is positive. So those are your conventions. So in the situation of the ball, okay, the ground is the reference point. the positive direction is up. That's going to be our standard convention for things. So we can define direction. Now, do I have to tell you what direction the negative is? In order to define my coordinate direction, do I have to tell you what the negative is?
Yes.
Not really. Because if I tell you that that direction is positive, that one has to be negative. Right? So I don't really have to tell you what the negative is. Negative is just the opposite of the positive. But I do need to tell you what direction the positive is so that you can have things defined correctly in your equations and in your graphs. Okay? Make sense? So let's think about a situation now of how this would be applied. Let's say that I am standing in the back of a truck and I'm hunkered down, and that truck is driving 50 miles an hour down the highway, going that way. So truck's driving 50 miles an hour down the highway. How fast am I going down the highway? 50 miles an hour, because I'm in the truck. Okay? So relative to the ground, I'm traveling 50 miles an hour. Now let's say I take this baseball and pull a Nolan Ryan and I throw 100 miles an hour that direction. If I throw it 100 miles an hour relative to me, then relative to you watching from the side, how fast is this ball going?
150 miles per hour.
150 miles an hour. Because relative to the road, before I throw it, it's traveling 50, and then I throw it 100 miles an hour faster than me. Okay? Now, if I turn around and the car is still traveling that direction, and I turn around and throw it 100 miles an hour that way, relative to you, how fast is it going?
50.
It's going 50. Because it was already going 50 miles an hour that way, and now I go 100 miles an hour that way. So the net result is 50 miles an hour that way. Okay? So when you have two different objects that are moving, you have what we call apparent motion or relative motion. If two things are moving, then there is a velocity or a speed that is relative between them. For example, if someone were to be running towards me at 5 miles an hour and I throw the baseball at them at 10 miles an hour, then relative motion would say that they're traveling 5 miles an hour this way, the baseball's traveling 10 miles an hour towards them, so from their point of view, the ball is coming at them at 15 miles an hour. Make sense? Because they're going 5 miles an hour towards the ball, and the ball is going 10 miles an hour towards it. So from their point of view, from their reference frame, the ball is coming at them faster. Right? Any of you athletes in here that have ever experienced when you're running towards the ball and the quarterback throws it at you, it appears to be coming faster than if you're running away from the ball, even if the quarterback throws it with the same speed. Okay? Make sense? Or when the linebacker is running at you, it looks like he's coming at you a lot faster than when you're running away from him. Okay? And hopefully if you're running away from him, then he's behind you and you're not just turning around scared. Because you wouldn't be starting very long. But so that's relative motion. So one more situation. Let's say I get in a boat and I start rowing down the river. And I'm rowing down the river 5 miles an hour relative to the water. So I'm going 5 miles an hour relative to the water. But that water is flowing 10 miles an hour relative to the bank of the river. And you're standing on the bank of the river. So when you see me pass, how fast does it look like I'm moving? Looks like I'm going 15 miles an hour. All right? Now let's say I turn that boat around. The water's still going that way. I turn the boat around. Now I'm rowing at 10 miles an hour this way. And the water, relative to the water. I'm rowing 10 miles an hour this way relative to the water. And the water's going 10 miles an hour that way relative to the bank. And you're standing on the bank. What looks like I'm doing? Looks like I'm right in one place. And you're standing over there and I'm like, hey, how's it going? I'm getting tired because I'm trying to go upstream. Right? That's why it's hard to swim upstream. Because you have to go against the water. That's relative motion. Once you can define your reference frame and understand that motion is relative, then everything else kind of makes a little bit more sense. We're talking about position versus time. Your position is where you are at a given time with respect to the reference point. Most of the time, I will just refer to the reference point as the origin. All right, because when we're graphing it, the reference point is 0, 0. Okay, so I will usually just refer to it as the origin, because we're going to do a lot of graphing of motion. If you haven't noticed, we've already done that. Okay? Now, in the last few minutes of class, before you leave, on a half sheet of paper, I want you to write down 3 things that you now know about relative motion that you didn't know before. Make sure your name is on it and turn it in.